Okay, and now for the NEAP short answer of the same exam. Okay, so let's have a read. First of all, with this exam, just keep in mind that the questions themselves, the chemistry behind it is okay, but as NEAP does, they've disguised them as difficult questions. Okay, first question. Over 30 million tonnes of the monomer chloroethene are produced worldwide annually. So we're obviously going to look at the production of chloroethene in this question. The first reaction in its synthesis using a particular catalyst is shown by the following equation. So the reaction has ethene. As you can see, there's only one way you can draw this particular molecule, and plus chlorine. Okay, so this will obviously be chlorine gas, and this will be an addition reaction. So the chlorine gas will add at the double bond, and remember that when it occurs, first of all, the double bond breaks spontaneously, okay, and we get what's known as a free radical on each side of the carbon. That is very reactive, and it will reform with the chlorine, producing no other products. So we just get two extra covalent bonds here, and we have added two chlorines to ethene to make it 1, 2, and name the product, so we'll name it here, 1, 2 dichloroethane, and we get the product that looks like this. All right, next one. The gaseous product from reaction 1 is heated in a furnace to 500 degrees Celsius at 30 atmosphere pressure to produce this second reaction. Okay, so the conversion is approximately 60%. So that talks about efficiency, and more importantly, the yield is 60%. Explain one change in conditions which would increase the percentage conversion. Well, let's have a look at this particular reaction. Now, we have delta H, which is greater than 0, which basically means that delta H is positive, meaning that we're dealing with an endothermic reaction. Now, for an endothermic reaction, we have pretty much the production of, the addition of energy. Okay. Now, we could change the temperature. For an endothermic reaction to be favored, according to Le Chatelier's, if we increase temperature, we will basically favor the reaction which partially opposes the change by absorbing the excess energy and this would be favoring the endothermic forward reaction, increasing yield. So we would increase temp. Okay? Because it's endothermic, increasing the temperature will move the position towards the right to partially oppose the temperature change. So this is really important. Partially opposes the change. Don't think that if you increase it to 550 degrees Celsius that it will somehow be able to decrease it back to 500 degrees Celsius just by favoring the endothermic reaction. That doesn't occur. So any real change, the change, just to keep in mind, will only be partially opposed. Temperature still higher than before the change was initiated. So that's sort of for your own benefit, but pretty much ending the question there. Another thing we can do, if you have a look, how many particles are on the right side of the equation and how many are on the left side of the equation. There is 1 on the left and 2 on the right. So basically, if we decrease pressure, okay, of course you only have to provide 1, but if we decrease pressure, the system will want to partially oppose this change by increasing pressure, by moving to the side with more particles, resulting in a net forward reaction and higher yield. Okay, so you would have to say that there are 1 mole of gaseous reactants here and 2 mole of gaseous reactants on the right, so it will shift to the right. Okay, state 1 disadvantage for the manufacturer if the new reaction condition listed in part I was used. Okay, so something you could say is, well, definitely with pressure, lowering the pressure lowers the rate of reaction, resulting in a smaller amount of product available per time. Something you can say about temperature is whenever we increase the temperature, we actually increase cost. So increased temperature increases cost for the manufacturer. Okay, so the HCl in the products of reaction 2 is recycled in a highly exothermic reaction, which is shown in the equation below. So produces a lot of energy because it's highly exothermic. Outline how the waste heat generated in this reaction could be used in the industrial manufacture of chlorine. So, as we said, increasing temperature will increase the rate of reaction because it's an endothermic reaction. So, what we could do is use the energy, you could even say the thermal energy produced in this reaction to increase the yield of reaction 1. Of reaction 1 or of reaction 2, this reaction. Okay, so you could say recycle the heat and use it for favoring a forward reaction in reaction 2. Okay, another method to produce chloroethene uses the highly exothermic reaction shown below. This method has many advantages over reaction 1 and 2, including high yield, higher product purity, lower cost for waste treatment. Given these advantages, suggest why one reason why chloroethene has been manufactured by 1 and 2 over the last 50 years. Okay, so let's have a look at the raw materials. Okay, so we've got raw materials for reaction 1 and 2 is ethene. And for this reaction, it is ethine. So I would just argue that ethene is a cheaper raw material than ethine. Okay? So basically it's cost effective for the manufacturer. So always think about it. Ethane is pretty easy to get our hands on. Ethene, pretty easy as well. But ethine is so reactive that it's quite hard to get our hands on. It's quite expensive. Okay, this example. Next question. As chloroethene is extremely hazardous to human health and is highly flammable, it is stored as a liquid in a high-pressure sphere surrounded by a larger sphere with a void space in between. Okay, so we haven't learnt any of this because good chance is NEAP is making it up. No, maybe not, but it's definitely not in the study design, so we're going to be applying our knowledge. Nitrogen gas is flushed through the space and analysed to detect any leaks of chloroethene. So basically, the void space, we have the chloroethene being stored here, and we have the void space which is not supposed to have any ethene, chloroethene. So why do they use nitrogen gas instead of oxygen gas? Well, that should just scream out to you the difference between nitrogen and oxygen. And nitrogen, it's not an inert gas, which would be the way you say helium or something like that. It does not participate in combustion reactions as oxygen gas does, and is a safer option. Okay, they gave you the answer when they said highly flammable. So it's highly flammable. That would be supported by oxygen gas, not nitrogen gas. So we all know about combustion reactions. So you'd have to say the term really combustion reaction to get that mark. So give yourselves a mark if you said that. All right, number 2. Outline how gas chromatography could be used to identify the chloroethene and its concentration when a leak is suspected. Okay, so basically you would have to describe how you use gas chromatography to identify a component, so how you use it qualitatively, and its concentration, so how you use it quantitatively. Okay, so what I would say is something like, for the qualitative analysis, so you would say compare a pure sample of chloroethene, compare, you could say, the retention times of a pure sample of chloroethene, right, to the substances emitted by the leak, and if a substance has the same retention time, it is chloroethene. Okay, to detect the concentration, I would say prepare standards of chloroethene and run through the GC, okay, and prepare a calibration graph to determine the conc of chloroethene in the gas leak. All right. So you could say then add in using peak areas or area under the peaks. All right, next one. Chloroethene is the monomer used to produce polyvinyl chloride. Okay, so we have chloroethene, and if you forget what that looks like, we have, that's dichloroethene. It's a monomer, so you can't really stuff it up. We have chlorine here. They tell you basically, well, you should know what chloroethene looks like anyway, but they tell you anyway the formula for it. So if these two join together, draw a section of it. You remember how to draw, you remember how to draw polymers. So it doesn't even say how many monomers you need to have, so you can do pretty much as many as you want, but important parts are, so say if we just draw two, no double bonds, they have added at the double bonds, and we draw open-ended bonds at the end, and you could even do a bracket and write N, showing that it goes on and on because it's a polymer. Okay, unwanted products made of PVC, polyvinyl chloride, are often discarded in landfill waste, leading to the formation of toxic compounds known as dioxins. For example, a dioxin with the formula blah 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 is produced during burning of the waste at low temperatures. Explain why dioxins are much less likely to form during high temperature incineration over 900 degrees Celsius. Okay, so basically you have to think about large molecules being produced at high temps. So we know about things just breaking down, okay? So pretty much at high temperatures, I would argue at high temperatures, the bonds in the molecule are more likely to break down, resulting in the production of smaller molecules and that's pretty much it, not the large dioxin molecules, or not large molecules like dioxin. Okay, so this one, question 2. Permanganate ions and oxalate ions may react according to the following equation. Relevant electrochemical data, blah, 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 shown below. So here we've got it in the same order as your electrochemical series. So basically we've got reduction, occurring here and oxidation at the anode. And this is at the cathode. Okay, write a balanced half equation for the oxidation process occurring in this reaction. Now, you would have to actually use this reaction, and we should know that oxidation, well, according to the electrochemical series, this is the reductant, which is oxidized, so we have to flip the reaction. So we will have C2O4, 2 negative, aqueous, going into CO2 gas. Now the first rule is we have to balance everything except for hydrogen and oxygen. And we've got 2 carbons on this side, we've got 1 on this side, so we have to add a 2 there. And then we've actually balanced for oxygen as well. So we've got 4 on this side and 4 on this side. Then we have to balance for charge, and we do that by adding 2 electrons to this side. Okay, so that was pretty simple. Explain why the E values provided indicate that a reaction should occur between permanganate and oxalate in an acidified solution. Okay, so I would just argue that MnO4 negative aqueous is a stronger oxidant reacting with a stronger reductant further down the electrochemical series, and therefore a spontaneous reaction should occur under standard conditions. So if you compare it, I mean, if we explain this, we know that a negative gradient will result in a spontaneous reaction, but let's make sense of that. This is actually a stronger oxidant than CO2. So if this reaction does occur and we get these products, Mn2 plus and CO2 negative, you get these two, they will not spontaneously react backwards. But you can imagine if somehow these two could react, they will produce, via electrolysis it would have to be, they would produce this and this, which would spontaneously react and go backwards. Okay, so whenever a strong oxidant is mixed with a stronger reductant, a chemical reaction is likely to occur. Okay, so MnO4 is a stronger oxidant than CO2. Remember, it's CO2 that's the oxidant. This is actually the reductant. And pretty much Mn2 plus is a weaker reductant than this. Okay, so then we have a look. A student mixed the required amounts and waited for the purple color, blah, blah, blah. No change was evident. Okay, so basically I would argue that like the hydrogen peroxide example, and that the data provided by the electrochemical series says nothing about the rate of reaction. So the reaction may be very slow under the conditions provided. Okay, under suitable conditions, the reaction was used to standardize a solution of acidified potassium permanganate and titration. So we've got a titration, a redox titration. Okay, so an aliquot used in the conical flask. Okay, and I mean, we can just draw a quick sketch. So we've got something used in the conical flask, C2O4, 2 negative, and it's at 25 milliliters. We have in our burette, this might actually help with errors. I don't know if there's errors on the next page. And we have 14.28 milliliters. And we also have the concentration, molarity. Calculate the molarity of the C2O4 solution used in the titration. Okay, so that's just using our moles, and got the calculator here. So, okay, so basically setting it up, N of MnO4, so using our known, equals CV 0.1575 times 0.01428. .0022491 mole, N of C2O4, and if you look at the mole ratio here, unknown over known gives us 5/2 times the moles of MnO4 negative, 5/2 times 0.00222491, 0.0056 mole, concentration equals N over V, divided by 0.025, and then that should equal and how many sig figs do we have? 4 sig figs, 0.2249 molarity. Okay. Next page. The table below shows possible effects of rinsing glassware used for the titration. Indicate if the piece of glassware was used to rinse with water only and not dried before use. Okay, piece of glassware left wet with water. The pipette. So the pipette was used to deliver this, diluting this. So we perceive its concentration to be lower than what it should be. So we perceive it to be the calculated concentration is higher than the actual value. Okay, so we are looking at the concentration of MnO4 negative, even though we was calculated to be, okay, that'll teach me. So MnO4 negative is this one, and this is the one we are calculating. MnO4 is in the burette. So the only thing that's going to make it lower than what it should be is rinsing burette with water, because basically we are diluting the MnO4 in the burette. And if we rinse it with water, it will be lower than what it should be. If we rinse the conical flask with water, conical flask, no change, because we are supposed to rinse the conical flask with water, because basically we take our moles from the pipette, so the pipette accurately measures out this. Now if you rinse the pipette with water, we are diluting this guy, so less MnO4 will need to react, giving us a higher value than we expect. So higher value, conical flask, same as actual, and burette lower. All right, question 3. The aluminium air cell is a possible future power source for electric vehicles, laptop computers, and mobile phones. A simplified diagram of the cell is shown below. As the cell operates, oxygen is reduced at the cathode. Aluminium ions formed at the anode react with hydroxide ions to produce aluminium hydroxide precipitate. write a half equation for the redox reactions occurring at the cathode. All right, so at the cathode, we're going to have the reduction of O2, okay, and basically it's going to be reduced to OH negative. Okay, but basically how you can do that is we've gone through the electrochemical series. I'll just grab that. We've gone through the electrochemical series and we've said that when oxygen's reduced, it's either reduced in an acidic solution to produce water, or it's reduced in a basic solution to produce OH negative. Okay, so we have O2 to OH negative, and we basically have this reaction that we simply have to copy out. Okay, and at the anode, so we've got at the anode, aluminium tells us aluminium air cell, so we have an aluminium anode, so solid aluminium going into Al3+, that forms a precipitate with hydroxide ions, so we have AlOH3 being produced. And let's balance this. Now you can go through all those steps of balancing with in a basic environment. So we'll do that. So balance for everything except for hydrogen and oxygen. Then balance for oxygen by adding water, and we need to add 3 of those. Then balance for H+ by adding well, we've got 6 on this side, 3 on this side, so we need 3 H+. Then we have to add OH negative to balance out and add it to both sides. Then this turns into 3H2O, and that cancels out. And then we need 3 electrons on that side. But it sort of makes sense because we have Al plus something will produce Al and OH3, and of course it's 3 hydroxide anions. Okay. The cathode is electrically conductive, inert, and coated in a catalyst. From the information provided, what other property must the electrode have? Okay, well, a big property that it must have is that it allows electrolyte, anions, and cations through, and a word for that is porous. Okay, so it needs to be porous, basically meaning that it needs to allow anions and cations through. Another thing you could have said is prevents reactants from moving through. Just like any galvanic cell, which converts chemical energy to electrical energy, the reactants obviously have to be separated into 2 half cells, the anode and the cathode, and basically that is because we don't want them to react just spontaneously in the one system, because there would be no transfer of electrons from one electrode to the next. Okay. The aluminium air cell has been described as part fuel cell, part primary cell. In what way is it similar to a fuel cell? Well, you can have a look. It says here that it's got moist airflow, although there's no aluminium that basically is constantly being supplied, because aluminium is just made up of the anode, and supposedly when this is all reacted, then the battery will go flat. But we have this continuous supply of oxygen, so you could say continuous continuous supply of oxygen to the cell, which is a reactant. And remember, the definition of a fuel cell is that we have a continuous supply of reactant. Why is it called a primary cell? Well, as we said, when the aluminium reactant at the anode is consumed, the cell will stop producing energy and cannot be recharged because products Al3+ produce a solid precipitate. Okay. An early problem in the development of the cell was the aluminium hydroxide forming a gel-like material on the anode. How would this affect the operation of the cell? Well, we said that basically this is, remember how we called this polarization? And we said that if the products build up around the anode, which we remember is the site of oxidation, the rate of reaction will slow down, and so will efficiency. Production of electrical energy is decreased. Okay. Aluminium hydroxide forms a powdery precipitate due to a special additive in the electrolyte. If the air cell is to be sustainable, the aluminium hydroxide will need to be recycled to produce aluminium metal for use at the anode. A chemistry student proposes that the aluminium hydroxide collected from the cell could be dissolved in acid to produce aluminium ions, as shown in the equation below. The aluminium ions could then be used in an electrolytic cell to produce aluminium metal. Analyze the viability of this proposal. Okay, well, let's have a look. Have a look at aluminium. Al3+, here we go. Aluminium ions. Okay. So aluminium aqueous. So what do we have in solution? We have Al3+, which is a possible oxidant. And this is the reaction that we want to occur. And what do we have as the reductants? What do we have as the competing oxidant? While higher up on the electrochemical series, and I should have really drawn this below, we have H2O, as you can see right here. So I would say not viable. H2O is higher on the electrochemical series and is a stronger oxidant than Al3+, and will be preferentially reduced. Okay. Would need, you don't have to provide any Okay, so Al solid can't be produced by electrolysis, by the electrolysis of an aqueous electrolyte. Remember, that's the same with Na+. It needs actually a molten electrolyte because it's a weaker oxidant than water and will not be reduced, which is what we want. Okay, aluminium metal is manufactured industrial by electrolysis in the whole cell. Okay, and with the overall equation being this, calculate the volume of carbon dioxide gas at 20 degrees Celsius temperature, and we have a particular pressure, which is in pascals. Great. Operate for 6.5 volts for 10 hours using a current of this many amps. So we have I, we have time, and we have V. Okay. So you might think, how are we actually going to answer these questions? We have a lot of information, but basically you could start off with working out the moles of electrons. Okay, so what we could do is work out the moles of electrons equals Q over F, and remember that Q equals IT, so it's actually IT over F equals 120,000 times 10 times 60 divided by 96500 equals 6.9. Oops, I did times 96500 times 10 times 60 divided by 96500 times 60. What am I doing? Okay, 120,000 times 10 times 60 times 60. Oh, here we go. 44767, and that's the mole of electrons. Now, to calculate the mass, what are we actually trying to find? The volume of carbon dioxide produced. Okay, so we have basically the mole of electrons that are going through. Okay, now to work out the mole of aluminium, we can simply use this equation. We know that aluminium exists at a 3+ and O will be 2 negative, and for it to go to Al solid, it needs to have gained 3 electrons. So this is actually the ratio between aluminium and Al3+. Similarly, we could have done carbon to carbon dioxide. Okay, carbon goes from a 0 to a +4. Carbon has to have lost 4 electrons. Okay, so we can do that. So we can simply go the moles of carbon dioxide equals 4/1 times the moles of electrons, 1/4, my bad, times the moles of electrons, equals 11192 mole. Okay, and we need to calculate the volume. So basically we use PV equals nRT. Okay, and we have the pressure in pascals, just so they're annoying, but we can easily go back using our data book value. We need to go to kilopascals. So basically, we are dividing it by 1,000. Okay, so we do 1,000 PV, so 1 times volume equals 11192 times 8.31 times temperature, which is 20 plus 273 as in your data book. Volume equals to change it to pascals divided by, change it to kilopascals. Okay, and we get a particular volume which is 2.7, and what's the two significant figures? Times 10 to the power of 1, 2, 3, 4. Should I just divide by 100? Times 10 to the power of times 10 to the power of 5 litres. Okay, so sort of a word of advice at this point is, if you're looking at redox reactions, okay, and particularly because here we've got a 1-to-1 ratio, carbon to carbon dioxide, kind of makes sense. You just compare the oxidation numbers to work out how many electrons they have lost or have gained. So in this case, we've got carbon to carbon dioxide, and we have 0, oxidation number of 0 to +4. So we've actually had to lose 4 electrons. So that's the mole ratio between number of electrons and the carbon. And aluminium, because aluminium is 2Al2O3 to Al, okay, we actually have A4. So we've got a +3 like usual, because we've got -2 over here, gives us -6, and +6 equals 0. And over here we have a 0. Okay, now in this case we've gone from each aluminium, individual aluminium has gone from a +3 to a 0. That means each aluminium would have to have gained 3 electrons, but it's just because we have 2 aluminiums, it's gained 6 electrons, but it's also made 4 aluminiums. Okay, so we have, but each aluminium has gone from a +3 to a 0. So the mole ratio, if we have the moles of electrons, the moles of electrons will be 3/1 times the moles of aluminium, or Al3+, same thing. Okay, so in this case, let's have a look at question 4. Compound in the table below have the same relative molar mass of 74, but have different boiling points. Okay, in terms of structure and bonding, explain why diethyl ether has such a low boiling point compared to the other two compounds. Okay, so diethyl ether, that kind of makes sense. Notice that it's an ether, so the ether linkage would look like this. just as quick revision, the actual compound would look like this. And this is actually the way you name ethers. I don't know if you remember, but we actually did do a couple of examples in that long sheet I got you guys to do. So we have this particular arrangement, diethyl, 2 ethyls coming off the ether. Okay, has such a low boiling point compared to the other two. So we have butanol and propanoic acid. So you would actually have to compare propanoic acid as well. So you would say they have low polarity and held together by weak dispersion forces, while propanoic acid and carboxyl both exhibit H bonding due to the carboxyl group and hydroxyl group respectively. Therefore, they have a much higher boiling point. Much more energy is required to break the hydrogen bonding compared to the dispersion forces. Alright, so let's just have a look at this one now. Got a few left, that's alright. So, the mass spectrum of butanol is shown below. In mass spectrometry, alkanols produce 2 characteristic fragments from the molecular ion by different pathways. We have alpha cleavage, which is where the CC bond nearest the hydroxyl group is broken, producing an oxygen-containing fragment. We have dehydration, in which a water molecule is eliminated, leaving an alkene-like fragment. Okay, and give the molecular formula of the oxygen-containing fragment produced by alpha cleavage of 1-butanol. So we've got 1-butanol, which looks something like this. Okay, and we remember that alpha cleavage, which they've probably made up, the CC bond nearest the hydroxyl group is broken, producing an oxygen-containing fragment. Well, that would give us something like this, okay, giving us a CH2OH. Now it says give the molecular formula of the fragment produced by alpha cleavage, so we would have to put CH2OH and plus, because we would only be able to identify it on the mass spectrum if it had a plus charge, lost an electron. On the mass spectrum above, identify the peak of the fragment formed by dehydration and mark it clearly with the letter A. Now in this case, you can simply determine the molar mass of butanol, which is, let's add it up, 12 times 4 plus 8, 10, sorry, plus 16 is 74. Now it says dehydration is where a water molecule is eliminated, so we lose H2O, which we know has the molar mass of 18. So we simply do 74 minus 18, 56. So we just have to find something with a molar mass of 56. So it would be this big fragment here. Because you can see 5246. There we go. Alright. The low resolution proton NMR is shown below of propanoic acid. Okay, so complete the table below to show the relative areas of each peak and the number of peaks evident. Okay, so if we have a look, relative peak area, number of peaks evident. Okay, now let's complete it. We have something at 11.8 we know is this H. Okay, so the number of peaks evident would be 1 because it would have no peak splitting because it's got a big fat blocker. That makes sense. Now, without even looking at the data book, I can just tell you the integration patterns. So we have a 3 to 2 to 1 integration patterns, and we have this one here, which would be here, and that makes sense. It requires more energy to flip the nucleus because it's close to a very electronegative element, which is dragging electrons from it, lowering nuclear shielding. Okay, so if you have a look, what is the peak splitting? So the thing at 2.4, the relative peak area we know would be 2, and the peak splitting, well, the carbon next door has 3 hydrogens attached, plus 1 is 4. Relative peak area for this one, okay, so this one over here, we've got 3, and peak splitting 2 plus 1 is 3. That makes sense. Okay, examine the infrared spectrum. Explain whether the spectrum shown is that of propanoic acid or butanol, 1-butanol. So it kind of screams out propanoic acid because, and you have to explain, there is, well, let's have a look at the data book. For carboxylic acid, we have definitely this big boy. We've got 1670 to 1750. There is, you have to say, propanoic acid. There is a trough at wave number 1670 to 1750, signifying a C double bond O group, and also you have to compare these two. You won't get the mark unless you compare these two. So we do have one at 2500 to 2300, and the other one sort of overlaps, although you just have to say it contains the 2500 to 2330 23300 trough OH of an acid, and not the 23200. Oh, and look, they've even done it nicely for you. So it doesn't actually have one at 3200 to 3500. Doesn't have one there, but it has one from 2500 to 3300. Like, it has one in this range. So it does not the blah 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 OH of an alk. Okay. Next one. An ester with the same molecular formula as propanoic acid. So what's the molecular formula of propanoic acid? We've got it here. Propanoic acid. Oh, also, don't forget that it's probably in your data book. No. Okay, so we have propanoic acid, which is C3H. Propanoic acid 6O2. Draw the structural formula of this ester. Okay, so let's have a look. We have 3 different carbon environments. That sort of makes sense. Peak area of 3, 2, and 1. So we have 1 hydrogen environment, and so 1 with 1 hydrogen, 1 with 3, 1 with 2. Alright, so I think we have enough info to do it. What are the possible esters? Well, we have this one. So we have methyl ethanoate. We also have, let's just shift it over one more. Ethyl methanoate. Do we have anything else? No. Okay. So, which one could it be? Now, this one would have 2 hydrogen environments. Already we've got 3. So it has to be methyl ethyl methanoate. Name the organic compound used to produce this ester with an alkanol. Oh, so what's the carboxylic acid? Has to be methanoic acid. So here we have the methanoic acid derivative and we have the ethanol derivative. Okay, question 5. Aluminium ions in an aqueous solution will precipitate when treated with a solution of hydroxyquinoline as shown in the equation to determine the volume of So 100 ml samples of the contaminated water. So basically, okay, so we're trying to remove Al3 plus from water. 500 litres of the contaminated water, that's our actual sample. And we've got 100 mils of each of these samples of contaminated water into 6 flasks with A to F. Different volumes of this were added to each flask. Each precipitate was isolated, washed, and dried. Okay, so in which flask A to F was the hydroxyquinoline solution in excess in the reaction mixture? Okay, so that sort of makes sense if you have a look at the mass of the precipitate collected. Okay, so basically we're reacting this, 100 mils of it, 100 mils of it with various volumes of this, and we have the volumes here, 20 mils, 40 mils, 60 mils, 80 mils, 100 mils, 120 mils. As you can see, when it is 60 mils, it makes about 22.5 grams of this precipitate, which is what we're measuring. Now, way to tell if it's in excess is if we add more, do we get more of a precipitate or do we get the same mass? Because it doesn't matter how much more you add. If you've added it in excess, you won't get any more product because it will be determined by the limiting reactant, which will be Al3+. So if you have a look, see, well, we can add 80 and we still get more. So really, it is just D, E, and F, because it doesn't matter if we add any more past D's amount, which is 80 mils. We don't get any more precipitate. So it's obviously been added in excess. Calculate the max amount of this precipitate formed in the 100 ml sample of contaminated water. So basically what you do is you get that mass of precipitate, which is 25 milligrams once, which would be the maximum mass produced from the 100 ml water. So the mole, and I cannot be bothered by that, but I will. Mass over molar mass, 25, but it has to be in grams, so times by 10 to the negative 3 divided by the molar mass, which is 459. Okay, and then you get a mole of 5.4 times 10 to the negative 5. Okay, and how many sig figs? Well, 3 sig figs. It's alright, lots of leeway here. So 5.45. Now calculate the volume of 0.1 m solution which would be needed to remove all of the aluminium ions from 500 liters of the contaminated water. Well, we have, we haven't tested it with 0.1 m. We've tested it with 0.00258 m. Now, a way you can do it is through the mole ratio. Sorry. So we have a particular amount of moles that we get. Now the moles of C9H7NO, NO required is 3/1 times the moles of precipitate equals 1.6 times 10 to the negative 4 mole in 100 milliliters. Okay, so we require that many moles in 100 milliliters. If we require 1.6 times 10 to the negative 4 mole in 100 milliliters, okay, X mole in 500 liters. So we have to change 100 mils to liters. So we times it by 10 to the 3. So we are ending up 10 to the negative 3. Ended up doing that times divided by alright, so just solving for X is 0.817 mole. Then to get the volume equals N over C, 0.817 divided by the concentration, and that would be in liters as 8.2 liters. Notice that our sig figs are now 2 because we have 0.10. Alright, complete the table below by explaining the procedures used in step 3 of the experiment. Answer these questions in the spaces provided in the table. Okay, so what is the purpose of washing each precipitate in step 3? Oh, that kind of makes sense. Removing soluble ions, which will increase the mass of the precipitate. What steps should be taken to ensure that the mass of each precipitate is accurate? Dry and weigh and heat to a constant mass. Okay. The original experiment was repeated 3 times, each time changing one condition. Tick any of these boxes in the table below to indicate which of the following conditions would produce a graph which plateaus at a high precipitate. So what's going to increase the mass of the precipitates? Okay. So if we use a high concentration, and no, because when we add it to excess, pretty much the limiting, if you think about what the limiting reactant is, it is the 100 ml sample, so the water. So if we increase the concentration of what we're precipitating with, it's already in excess and it produces a maximum mass of 25 milligrams, so that's as much as we're going to get. 150 ml sample of contaminated water, well, definitely. Each precipitate was washed several more times than originally. If anything, that will decrease the mass, so no. Alright, so the Ka is 1.58 times 10 to the negative 9. Write an equation showing the ionization of it in water. Well, that's easy. C9NO plus H2O, and it's a weak acid because we've got a small Ka, equals, and pretty much just removing one H, just like writing the conjugate base, H3O plus. Write an equilibrium expression for the reaction. Okay, so Ka equals divided by C9H7NO. Okay, now calculate the pH of a 0.3 m solution at 25 degrees Celsius. So what are we assuming here? We are assuming that H2O plus equals this, i.e. the dissociation or the self-ionization of water is negligible, and we are also assuming that initial concentrations of equals final equals equilibrium concentrations. So this sort of makes sense because we're not given pH, and when we're given pH or the products and the initial concentration, then we don't have to make that assumption, but now we sort of need to make that assumption. Okay, so calculate the pH. Well, we've got the Ka 1.58 times 10 to the negative 9 equals x squared, because these two values will be the same, and that's what we're trying to find out, divided by 0.3. Okay, and then we just pretty much solve for x, which will be H3O plus. So the concentration of H3O plus times 0.3, square root of answer, 0.1234. Now pH negative log times 10 to the negative 5. And that's 4.7. Okay, so that makes sense. Alright, now here we've got a HPLC question. Alright, now the fermentation process to produce the biochemical fuel ethanol, known as bioethanol, can be monitored using HPLC. A chromatogram for the fermentation is shown below. Write an overall equation for the fermentation of glucose to form ethanol. Oh, that kind of makes sense. C6H12O6 produces, you guys should just know this one off by heart. Okay, so that one we've done plenty of times before. And on the chromatogram, draw in one significant change to any peak which is likely to be evident after 24 hours of fermentation. So after 24 hours, let's just see. Well, 3 would be definitely lower, and 7 would be higher. Okay, and let's have a look at these ones. Identify 2 correct statements about HPLC. Alright. Increasing the temperature will not change the retention times. Of course it does, because increasing temperature decreases retention time because they elute faster, because they're more likely to be in the gaseous phase or the more volatile phase. Okay, doubling the volume will double the retention time. No, remember, it will just change the area under the peak. Area under peak. Using smaller stationary phase particles will increase the retention time of the components. Yes, it makes them take longer to get out because they have to swivel through the smaller components. The component most strongly absorbed is ethanol. It has the longest retention time, meaning that it's absorbed most strongly, which is most likely because of its hydrogen bonding, but yes. A mobile phase of a different polarity will have no effect on the retention times, no way, because it is attracted to the stationary phase, okay, so depending on how polar it is. So here we might have quite a polar stationary phase because we have ethanol, which is taking longer to get out. Once a component is absorbed strongly into the column, no desorption will occur. No, that's just false. Okay, so peak 1 is produced by dextrins. Dextrins are a short chain of glucose. Draw and name a linkage between glucose units. Ether. And in other words, glycosidic, because in this example it's between 2 glucose molecules. Remember that you can only call it glycosidic if it's between 2 monomers of carbohydrates. Peak 2 is produced by maltose. Maltose is a disaccharide formed by the condensation of 2 glucose molecules. Write the molecular formula of maltose. Okay, let's have a look. Maltose, 2 glucose molecules. Okay, so we've got C6H12O6 plus C6H12O6, but remember when they're formed, it's via a condensation reaction, so we have to minus H2O from the final one. So we will have C12H, we will have 24, but we'll actually have 22 because we have to minus 2 H's. O, we will have 12, but we'll actually have 11 because we have to minus 1 oxygen, so we'll need minus water. Okay. The bioethanol produced by fermentation is seen as a replacement for petrol, as in fuels in cars. Petrol contains high proportion of octane. By calculation, show that the amounts of carbon dioxide produced by each amount of carbon dioxide produced for each kilojoule of energy released in both bioethanol and octane is almost identical. Okay, so for this particular one, we can use the data book because we have octane. Now, octane, for 1 mole of octane, we release 5464 kilojoules. Okay. So 1 mole releases 5464 kilojoules. Now, if you have octane C8H18, it will release 8 carbon dioxides. So, for each kilojoule of energy. So, I would just do a ratio. Alright, 8 CO2s are released when 5464 kilojoules are released. X CO2s are released when 1 kilojoule is released. 5464. Okay. So we have 1.46 times 10 to the negative 3 mole of CO2 per kilojoule. And we do the same for ethanol, which is 1364. The ethanol is a C2, so it releases 2 carbon dioxides. So 2 CO2s released when we get 1364 over 1 over X, 1 over 1364 times 2, 1.47 times 10 to the negative 3 CO2s per kilojoules. And then you'd have to have a little statement, almost same as octane. Okay, so the carbon dioxide gas released from the burning of octane is much greater environmental concern. Okay, I'm just going to read this one out to you, or you guys can just have a look. It's kind of obvious. So the carbon dioxide from octane is from a fossil fuel and contributes to the increasing concern of CO2. But with the biochemical fuel, you have to say that the amount taken up initially from the atmosphere is produced when burning it, or in producing it as well. Therefore, it is carbon neutral. Okay, question 7. An electrolytic cell. An electrolytic cell is set up using copper electrodes with aqueous electrolyte containing Pb, Ni, and Mg. A current must pass through the cell. Outline the sequence of events occurring at the cathode, including what happens to each metal ions during electrolysis, including any relevant half equations in your response. So, what type of oxidants do we have? And in order. You should always write them in order to save you time. Okay. Well, the question says we've got Pb, Ni, Mg. Pb is about here. Ni is here. Mg. It's aqueous, so we also have H2O, and that lies between Ni. Okay, so outline the sequence of events. Basically, you'd have to say something, and we've done this similar example before. So reduction occurs, so therefore Pb would be reduced first, and Pb 2 plus 2 electrons to Pbs, then nickel, then H2O preferentially reduced. You would have to provide the half equations for all of these, but I can't be bothered. So then H2O preferentially reduced to produce hydrogen gas. Then that would stop the production of Mg solid, because we've got so much water in the cell that it would just keep being so much H2O in an aqueous environment that it would keep being preferentially reduced. Write the half equation for the initial reaction occurring at the anode. So anode, we have oxidation. So we have reductants. So what reductants do we have? We have copper, and we have H2O. So basically we would have copper, this reaction, copper producing copper 2 plus 2 electrons. Okay. The student wanted to investigate the factors which affected the amount of copper deposited during the electroplating. The following experimental procedure was used. Okay, just read over that. Okay, critically evaluate the design of the experiment. So, in evaluating this experiment, you would have to look at them. A, B, C, and D, using 4 different cells. Now, what are we actually looking at here? We're looking at the temperature, we're looking at the concentration, and we're looking at the surface area. So, really, when you compare factors affecting another factor, you need to keep all of the conditions the same besides the factor under investigation, which is your independent variable. So in this case, what can we actually compare? Well, let's have a look if we've got temperature, 20 to 30, can we compare that? No, because we changed the concentration as well. Can we compare 30 to 40? No, because we changed the concentration as well. So we can't really compare temperature. Can't compare temperature, and you would have to explain why. Okay, can we compare concentration? Only in cells C and D. Cells C and D can compare concentration because C and D keep everything the same except for concentration. Can we compare surface area? No, because the conditions change. So really it's only C and D which are comparable, and they will tell us about concentration. Outline 2 changes which would be made. Okay, there's plenty of things here. Basically, if you want to compare temperature, then keeping the concentration and surface area the same. So keeping the concentration at 0.15 m for cells A and B or something like that. I'm sure you guys can do that. Okay, question 8. Finally, when H2 and I2 were introduced into a sealed container, equilibrium was established according to this equation. Okay, so we have this particular equation occurring, and we have the concentrations tracked over time. This is not new to us. During the time interval of 0 to 200 seconds, the temperature was kept constant by removing heat from the container. So that just screams to me that it is an exothermic reaction. But anyway, explain how it can be demonstrated that chemical reactions are still occurring during a state of equilibrium by introducing into the system a trace of radioactive isotope deuterium. Basically, if we put in hydrogen, but it's radioactive now, okay, that's going to be the H deuterium will be introduced into the reactants and products and will be detectable and detectable in the products and reactants as H2. Okay. Calculate the equilibrium constant which occurred in the time interval 0 to 200 seconds. So we have K, which is HI divided by H2 over I2. Calculate the equilibrium constant from 0 to 200 seconds. So here we have concentration of HI at HI squared equals 0.04 squared divided by 0.08, not 0.08, 0.09 times 0.06. So 0.04 squared divided by 0.09 times 0.06 gives us an equilibrium constant of 0.296. To two significant figures would be 0.30. At t equals 200 seconds, a change was made to the volume of the reaction vessel. Outline what change was made and indicate the magnitude of the change. So it was definitely, it decreases concentration. So the volume must have been increased. Okay, so let's work out by how much. Now, the way you can do it is just by comparing one. Let's grab, iodine, for example. I2, it goes from a concentration of 0.06 to 0. And it's not exactly on 0.05, it would be 0.053. So basically 0.06 okay, we do 0.06 divided by 0.053, so it actually increased by a factor, increased by 1.13, a factor of 1.13. Alright, so next one. Circle one of the following to indicate the value of K at 560 seconds compared to 260 seconds. So 560 compared to 260, so compared to here, what has happened? Well, that's kind of obvious. The reactants have both increased and the products have decreased, products being on the top, so therefore K has decreased. So K is lower. Without any calculations, explain your reasoning. So the concentration of reactants has increased and products has decreased. Therefore, the denominator is greater, leading to a smaller K value. Alright, last question. The experiment was repeated under identical conditions, except that a catalyst was used. By drawing a line on the graph on the previous page, show the effect of the catalyst on the concentration of HI. Okay, so basically, you've done this one plenty of times. We are just increasing the rate at which it's produced, so we just bring that out a little bit further. Okay. So when a catalyst is introduced, we're looking at over time the concentration of it being produced, and that's just increasing. But we do not change where it falls on equilibrium, because catalysts don't change yield increased rate of reaction only. That's important. Okay, well that's pretty much it. Okay. Sorry, just one more thing. They don't change yield, but they increase the rate of reaction. They increase the rate at which they make things reach equilibrium faster. But then once they're at equilibrium, the concentrations of the forward and reverse stay the same. As we know, they plateau off over time. It's not increased anymore at equilibrium.